Thank you, Al. Hey, everybody. So I'm going to talk a little bit about, a project called, what I call the Mega 2E. So I found out about this chip that Apple put into one of its computers, and they never bothered to make a product that used it how they intended. And so let me give you a little bit of background. Let me just ask, how many people here have ever used an Apple II computer? Okay, I'm going to go real fast then. So in 1977, Apple introduced the Apple II. The most impressive thing to me for this talk is it had about 80 chips in it, and except for the ROMs, every single thing you see on the board is completely off the shelf. Everything outside of the blue boxes, those are mostly 7400 series logic and a couple of 555s. Its follow-on, the Apple IIe, consolidated almost all of the general purpose logic into 3 chips: a memory manager, an I/O manager, and a timing generator. Now, the MMU and the IOU, those also incorporated some new functions. So you could plug in a 80 column card and get this, then get 80 columns on the display. Now, the Apple IIc is basically the Apple IIe without expansion slots and a bunch of stuff built in. The key thing I wanted to point out is it had a chip called the IWM, or the Integrated WAS machine. So that was the DISC-2 controller that all of the Apple IIs used up until the IIc as a single chip. Also, the IIc incorporated a slot-based power supply. Both of those things will be apparent why I mentioned them later. Now, the 2GS is a very different Apple II. All of the others were 8-bit 6502 based. The 2GS is improved in almost every single aspect. In fact, the G and the S stand for the better graphics mode, and the S stood for the fact that there was an actual sound chip inside of this thing. Now, what's sad to me is this computer came out in 1986, and it had elements of desktop computers, or had elements that desktop computers would have for decades afterwards. And despite the advanced for its time capabilities, almost everyone, especially schools, used it to run 8-bit Apple II software because it was almost entirely backward compatible with the previous generations. Now, we're going to dispel a couple of myths. But first, the reason people thought that it had that compatibility was a chip called the Mega 2. The Mega 2 combines the MMU, the IOU, the character ROM, and the video generator, including the 80 column stuff, into a single ASIC. So Apple basically went in about 9 years from 70 to 3 to 1 chip. Now, I have no data sheet for this chip other than its pinout in the schematic. This is about the closest I can get to documentation, in which Apple's own documentation says that other than RAM, ROM, and a CPU, it is a single chip Apple IIe. Okay, that's lie number 1. It's actually in the sentence. You need 3 other chips to make it work anyway. And then the second one is, this actually has nothing to do with the 2GS's backward compatibility. Now, it does control the I/O slots, so maybe we could say it was responsible for hardware backward compatibility, but the 2GS had everything built into it, so you didn't really use the slots that often. And its other function was to do video modes, well, the Apple II video modes. The 2GS video modes, its controller used the Mega 2 as a memory controller. Software did not, quote, run on the Mega 2. All of the software hooks were built into the 2GS's ROM and the 2GS's chipset, which really led me to wonder, number 1, was this chip ever finished? Because the rumors are Apple was going to make a computer based on the Mega 2 as a cost-reduced 2E. But what if that project got canceled, the chip was never finished, and the engineer said, we just need an I/O controller, it'll work great in this 2GS. So I decided, I decided to start over. So I wondered, could you remove the Mega 2 out of a 2GS and make a fully functional computer with it? So that's what the rest of this talk is going to be, is my journey to figure this out. And if you've watched any of the about 1,000 hours of live streaming I did for this project, you already know the answer. Now, halfway through the project, I learned about this annoying little hiccup in my quest. Tiger Computer Corporation, or Tiger Electronics, released the Tiger Learning Computer as a test product. It was canceled during test marketing. They licensed the Apple II design and the Mega 2 from Apple. So David, who provided these pictures, tells me you can get to an AppleSoft prompt with this computer. But I already know there's at least 2 versions of silicon for the Mega 2, and I don't know what is in this one. So it's great that it exists, but there's only like 10 of them in the world. I mean, there's a few more, but there's not a lot. There's also this chip called Gemini, which is found on something called the Apple IIe expansion card. It was for the Macintosh LC, so that the Macintosh line could run Apple II software. Some people have mistakenly said that this is a Mega 2. It's not. First of all, it's in the wrong package. Second, it came out like 4 or 5 years after the Mega 2. And third, I did find a partial data sheet for this one. It not only has some functional differences, like how it talks to the LC, but it also has at least one register that the Mega 2 does not, which is really unfortunate because then I could have an Apple IIe that runs at 2 megahertz, but that's beside the point. And then there's also something called the video overlay card, which I've never actually put my hands on. Now, none of these 3 things answer my question. Can you take out a Mega 2 and make a computer out of it? So here is totally the first attempt I made because I said, number 1, there was nothing before this, don't ask. So in the upper left, or on the top, I have a board that has the Mega and the DRAM. One quick thing I need to tell you about the way that the Apple II clocking system works is the CPU is clocked at 1 megahertz, the RAM is clocked at 2, or approximately. Half of that 1 megahertz clock is so that video can deal with RAM, and the second half is so that the CPU can deal with RAM, okay? That's important later. I connected that to a CPU card with a modern WDC65CO2 and a relatively modern electrically erasable EEPROM. Now, for video, I didn't want to get into how the video stuff works at this stage in the project, so I copied and pasted the Apple IIGS schematic, the video schematic from the BitPreserve project, and just recreated the video board, which actually worked really well. I used it for almost a year and a half. It was great. So on that EEPROM, I put the Apple IIe ROM, and on the very first try, I got this. Oh, wait. I got this. So this was about 6 months into earnestly working on this project, and this was a high and low at the same time. It was a high point because it looked promising AF. Right? If you know anything about the way that an Apple II boots, this looks extremely familiar. The low point was I could not figure out a viable reason why the Apple II string was duplicated. Nor could I understand why this other junk over here was happening. And I think it was months, but it was probably more like weeks, debugging the hardware, trying to figure out what was wrong with this, and I could not find the problem. That's the low point, because then I started to think maybe I was right. Maybe the Mega 2 was never finished. Maybe this is why, because like if I look at the logic analyzer, it's just jumping all over the place. So it's getting very confused very early during boot, and I can't figure out why. So no joke, I was talking to my friend Rob about just giving up and saying, you know what, it's not done. And he said, you know, I built a 6502 once, and I had something like this happen when one of the data bits was stuck. And I was like, well, I looked at the data bus, I didn't see anything, but I said, okay, fine. So I went probing around with a scope on one of the RAMs, and most of the signals looked like the one in the middle, which is relatively good. You can even see read and write cycles happening. One bit, however, was on the right. And even if you can't read an oscilloscope screen, because it's red, you know that's bad. So then I pulled out a microscope, an optical microscope, and I found, if you can see it, there's a orange sliver. There was a copper wire that got stuck in the flux residue, which also explained why some days the pattern was different. It was like the humidity in my lab would determine how conductive that was. So I cleaned that up, and I got to this point. So the upper right-hand screen, I'm using OBS to capture that analog video board, and so I turned it on. Okay, I'm laughing maniacally. Unfortunately, you can't hear it. Yeah. So at this stage, we were well into a year into the project, and I got this. So what did we just see? In the Apple IIe ROM, it has a diagnostic routine which was meant for manufacturing test. And so it ran through its test and said, hey, everything looks good, which makes no sense because it's just a pile of wires. But it was the first time where I'm like, oh shit, this thing might actually work. Because even though it's not a comprehensive test, it hits a ton of stuff inside of the Mega 2. So I was a little excited about that. I think this is the first and hopefully the only time that I've ever cried on camera. But why did it go into the diagnostic routine? Why didn't we go to the Apple II prompt? So I need to explain in the Apple II, in the C address space, so C0, pretty much XX, there is something called soft switches. And this is where you can basically or you can either write or read to these memory addresses and change things in the computer or get settings back or get data back. So for example, if you want to change to graphics mode, you hit a C switch, it switches. Now, in this case, on the far right side, there's a call to C062, which is called button 1. And basically, that is checking the Apple keys on the keyboard to see if they're pressed. One of the first things the ROM does when it boots is check to see if the user is pressing those keys so that it can alter the boot behavior. If the keyboard is not present, it's supposed to go into its diagnostic mode. Now, if you remember earlier, I don't have a keyboard. So I patched the code to jump over this stuff, and I got to this very promising screen. At this point, we're really far into boot. However, we're crashing, and we're crashing into the monitor. And so for those that don't know, in the 1980s, or early computers, they had a program built into ROM called the monitor. The monitor allowed the programmer to read and write memory addresses. Programmers used it to debug their code, and gamers used it to cheat. So if you look at the very top line, ERR, that's code for bad. Below it, 0002 is a memory address, and then you see A, X, Y, P, S. Those are status registers in the 6502. What I'm interested in, though, is that asterisk, because that is where the user is supposed to input commands. And you'll notice there's a whole bunch of junk on that line. So something is typing into our keyboard that doesn't exist. So to quickly explain why, this is the block diagram for an Apple IIe. On the very far left, we have a keyboard matrix, the thing you press. It's controlled by a microcontroller, which ironically is a 6502. It decodes the keyboard matrix and then drives the ROM. That ROM is basically a lookup table between the keyboard matrix and ASCII values. So when you press A, capital A, it puts 7 bits of 65 out onto the data bus. It's activated by the MMU chip by a signal called KBD. So basically, it activates the output enable of the ROM drives the bus at the correct time. 2 other quick signals, the keyboard controller also has any key and key ready. Those tell the IOU if you've pressed or held down keys or something like that. Now, the problem with the challenge with that KBD is it's only one half clock cycle. So you got about 400 nanoseconds to detect it, get on the bus, drive it, and get back off. And initially I thought I'd use a microcontroller, but I couldn't find one that could respond to interrupts fast enough. However, the RP2040 and its PIO can. It's a state machine that runs asynchronous to the ARM cores. So I programmed it to respond to the Apple II signals. And it could easily drive it. And so in the Apple IIe, I programmed this Pico to basically accept characters over serial and then type them on to the Apple IIe. Super fun. The problem is the Mega doesn't have those signals. It did have cleverly named signals K select 1 and 2, K being keyboard. At first I thought, oh, this just must be the Apple IIe keys. They named the pins different. Isn't that cute? I was wrong. But what I did notice is when I watched the logic analyzer and saw the keyboard get pulled, these always assert it. So I programmed the PIO to at least drive a null character when it saw these assert. And that got me to a stable boot prompt. So at this phase, I'm all excited because I really, really want to see what this thing can do. The problem is it looked like this. And I'm not exaggerating. I know I exaggerate a lot, especially for effects sometimes. Every single time I moved a wire, it was like 5 minutes to get it back to that same state. This was not a tenable situation. So I came up with a new modular platform. And the idea behind this one was that I wanted to be able to test blocks of the Apple II circuit and not have to spend a bunch of money respinning a massive prototype board. So I came up with the backplane and then the cards that plug into it, including a new CPU card, which was basically the Rev 1, but integrated all together and fixing a lot of mistakes and misconceptions that I had. I also just wanted to point out, I made this really cute proto board, and I have never used it, which really makes me sad because it was really fun to make. So the idea is you plug the CPU card into the backplane, and then you plug the other cards into the slots. Now, 2 questions usually come up. Number 1, why didn't I use edge connectors? Really, I just didn't think of it. In my mind, I wanted the pin headers because I wanted more places to clip my scope probes to, and I thought if I had to bodge things, then I have extra points to bodge to. In retrospect, I should have just done a card edge. And then the other is this compatible with Apple II cards? And the answer is no. This is a hardware development platform. And so that bus is grouped together to maximize debuggability, including, if you look at J3, the big connector, you might wonder, why did I group the address and data bus in these groups like this? It's because I wanted to be able to plug my logic analyzer directly into the backplane. Of all the things I did in this project, I feel like this was the most clever thing I came up with. Because this, it eliminated 30 fly wires right off the bat. It made it, the signal integrity was pretty good. The digital discovery is actually not great with 5-volt systems because it's got like a less than 3-volt threshold, so it picks up noise really bad. It's still highly usable, but every once in a while I was like, is that real? And because it was there, it was just so easy to just always be able to debug. Now this is the same stack up at a different phase in the project. I just wanted to show the cards real quick. So the card that's in the front has a chip called Slot Maker. And then Slot Maker came from the 2GS because in the 2GS it allows you to select either the internal stuff or the slots. I'll explain why I have it in just a minute. Behind it, it's connected to my version of the disk card. So that IWM chip that I mentioned, I incorporated that into my own card. In fact, you can see a gray ribbon cable. It's connected to a floppy emu. That's just a modern floppy emulator. And then behind that is one of my keyboard interfaces based on the PIO stuff that I showed earlier. So I'm gonna jump around in my timeline, but that Rev 2 stack up did get to a point where it could successfully boot from floppy disks. This was probably one of the most exciting things, one of the most exciting points in the project because I could really start moving fast. Also, I just wanted to point out, if you've never heard an Apple II boot, you really need to. It is it's super loud, but it is also somehow soothing to hear it seek track 0. And most of the time I use the emulator anyway, but okay, so I want to back up. I want to talk about that keyboard because the keyboard actually, I found a bug in the Mega 2. So I mentioned Slot Maker earlier. One of the things that bugged me early on was why did K-Select start with 1 instead of 0? And the answer is it didn't. K-Select 0 comes from the Slot Maker chip. Now remember, the Slot Maker chip controls the slots. It has absolutely nothing to do with the keyboard. The only literal reason I can come up with why they did it this way is they ran out of pins on the PLCC, and the Slot Maker connects by a demuxed bus. So I think they were able to mux it into there and then get the signal. So I just want to point out that the single chip Apple IIe, which needs RAM, ROM, a CPU, also needs a custom ASIC called Slot Maker for one stupid signal. And you need a keyboard controller. I don't know about you guys, but I don't think that's how you count single, but. Now, so here's the thing. With K-Select 0, I could tell the difference between the 2 C switches. I'm sorry, I always call them C switches. They're actually called soft switches. The difference between the 2 soft switches that dealt with the keyboard. With that, I was now able to modify my PIO to correctly respond, and then with tiny USB, I got to the point where I could use a USB keyboard. So the left is analog capture. or capture from the analog video card. The green is a serial terminal to the RP2040 that's controlling the keyboard, which for months, I actually did everything through serial, which was really kind of fun because I used my, super modern laptop as a dumb terminal to an Apple II. And the super cool thing is because the Apple II keyboard is entirely ASCII, except for the open and closed Apple keys, everything worked. It was really cool. Except, now that I could run a lot of software, I started running into programs that would crash during boot. And I couldn't figure out the commonality between them. The only thing I knew is that during boot, they would crash. And so for a while, I researched the disk drive stuff because that seemed like the most logical thing. Total red herring. This was entirely related to the keyboard, which Frogger was the easiest program for me to reproduce the problem. So after spending a lot of time with the logic analyzer and several adult beverages, I noticed, seriously by accident, that on the address line, we hit C0002 and case select asserted, which it shouldn't have. And that really bugged me for a long time because I'm like, well, this can't be the real problem because the 2GS would have had this problem. Here's what's going on. As the address lines are transitioning during a transition state, the Mega matches its logic and asserts case select. The reason it works fine in the 2GS is because the 2GS uses a chip called keyboard glue to qualify the signals during the CPU phase. Remember I said that both the video and the CPU get access to the data bus at the same time. I was driving the keyboard during the video phase when I wasn't allowed to. Here's the problem with that. So here's why it was happening. In the PIO, I watched for the clock to go high, which indicated to me I was in a data phase. Then I checked case select to see if I should do something with them. Does anyone see the problem? When phase 0, that signal goes back low, I'm still watching case select. Now, the issue I ran into with the PIO, you only get 32 instructions. Guess how many I'm using right now? 32. Now, I do have to point out my friend Tim helped me quite a bit to optimize this code because initially I didn't think I could even get this to work. Now, he thought he might be able to make this work. I think he could have done it, but I decided to channel my inner Steve Wozniak and think, how could we fix this in hardware without adding a bunch of chips? I didn't want to add a whole bunch of AND gates to try to figure out what was going on. And then it hit me. I have to do a logic transition anyway because 5-volt Mega logic can't connect to the RP2040. I was using a bidirectional shifter to accommodate that. Or is that one bidirectional? No, I don't remember. Anyway, I was using a logic shifter. So I just replaced that with a latch, an LVC, and drove that with phase 0, and it worked. Now, what I wanted to point out here, what was really fun for me is this was the 3rd revision of the keyboard controller. And when I got it back, I made 0 changes to any of the code in the RP2040, and it worked fine. Yeah. Okay. You have to remember, I'm going through a whole bunch of capture devices, so there's a delay. That is why I died in all the games I played. Speaking of that, I was still using that stupid analog video. I wanted to get rid of it. Now, I'm going to go fast through this because I could have actually talked the entire time about how this video stuff works. In the Apple IIe, there's a signal called serial video, which is the chroma and luma data for one line of the screen. You combine that with a color burst and a sync, and that's how you get a composite signal out of it. The Mega 2, however, it does have that signal, but in the 2GS, they don't use it. Instead, they use this 4-bit bus called RGB. Right? So RGB is 3 and it's a 4-bit bus. It's because it's a 16-bit lookup table. And so what's going on is it's actually demuxing Servid into a parallel bus. So if you clock in those 4 bits at 14 megahertz, you can recreate a frame of video, which is basically what I decided to do. Otherwise, you have to do a whole bunch of stuff to figure out what phase you're in on the Servid and blah, 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 blah. So I used another RP2040. If you want to know why, it's because I ran out of pins. I couldn't do it with both. The one thing I wish the RP2040 had is more pins. So with one core, I capture the data, frame it up, put it in a frame buffer, and then with another core, I found a library called PicoVGA that does a whole bunch of cool stuff that I hope to use someday, and spits out VGA. I only want to point out that at this point, I made about 20 PCBs in the course of this project. And this is the first one that came back on its first revision, that came back with no bodges and powered on the first time. So I think that means from now on, I'll never have problems, right? In terms of the video quality, it is a remarkable improvement over composite. But I wanted to point something out. If you're familiar with Apple II video, one of the characteristic things about its color modes is that they're entirely shit. And so on the left, the score is supposed to be all white, but you get this fringing effect because of the way that the Cervid signal generates the composite video. But notice how my screenshot on the right has the same fringing, even though I am capturing the signal completely digitally. The Mega 2 actually generates that fake fringing. And this was actually, I wondered about that for a while. Sorry, I'm going to tangent real quick. So the one thing that's unique or interesting to me about the way that the Mega 2 does its video is it doesn't matter what video mode the Apple II is in, it always outputs stuff at 14 megahertz. That's not entirely how the IIe circuit works. And I think this is why, is because it has to emulate this mode. Okay. So with that, Rev 2 was done. Now, I also did an audio board and fixed a couple other things and stuff, but I had a functional Apple II, even though it was a little bit of a mess. And by the way, I don't ever plan to take this apart except for, well, when I get back home and I put it back together. Because this is a fantastic development platform. I almost want to recreate this for the actual IIe itself because I can probe anything and it's super fun. But I wasn't done yet. My original goal was to make a portable Apple II, but then I just decided I wanted to make an Apple IIe-compatible computer. I didn't care about the portability. However, I thought it'd be fun if I could make it cute and small. So I took all of those boards that I designed for Rev 2, consolidate, put them all together in one project. Fortunately, I don't talk for a living, so I put them all together in one project, and then basically went to town on it. Now, I used the best auto router in the world, the human brain, and came up with a PCB layout that I like. So this has all of the functions of an Apple IIe, plus the IWM, plus the RP2040 stuff, so USB keyboard, VGA out. I also have keyboard control of the audio. And then on the top, if you're wondering, that blank spot, that's where the power supply plugs in. That's why I said I really liked how the 2C did that, and I decided on this one, like someday I want to make this work off of, say, USB-C or something, so that way I just have to respin the power supply board. Initially, I thought I was going to do it in 2 layers. I almost went to 6. I mean, this was one of those things that was really funny to me because I posted this picture on Twitter a long time ago, and certain people just flat out said, "Oh, you can easily do that in 6, or easily do that in 2." I'm like, what the? I was like, I didn't even have the rat's nest turned on. How could you possibly know? No, you can't. You have to make it bigger. Anyway, okay. However, a couple of things happened. First, the boards I got back from the first fab were clearly wrong, even though they lied about manufacturing them wrong. The second set of boards seemed to go well, except this is VGA 2040, not locking onto anything. And I couldn't figure out why for the longest time. I have a video coming out in a couple of weeks, and you'll get to experience my actual frustration with this problem. Basically, what I figured out is nothing was driving the data bus during boot. The only thing that should be driving the data bus right out of boot is the EEPROM. So I went and looked at its schematic. Let me know when you find the problem. Let me help. So, who noticed pin 31? Who noticed pin 25? Yeah, so for those that don't know, WE is write enable. I've tied it to ground, so that means my read-only memory is stuck in write mode. And then for reasons I will never understand, I tied output enable to high. This is also active low. So it is impossible for this chip to ever drive the data bus. So with a few choice words and a couple of hours of torture, if you look very closely, you'll notice I made a few changes to the circuit. That's right, I added caps on tape. Yeah. Yeah. Well, it's kind of, oh, that was going to be bad. It's kind of right here. Yeah, I just got to a point where I just said, F it, I'm soldering the thing to the board. But eventually I got it to boot. Now, this is just one demo. I'm going to show you a couple more in a second. So this is a basic program that turns the annunciator bits, there's 4 outputs, into a binary counter. I just thought, of course, it's a project that has to blink LEDs, so I made sure to do that. I didn't mention it earlier, but the 8 LEDs above that, those are actually the upper 8 address bits, and that was actually one of my biggest clues when I was first turning it on that something was wrong, because they were not going through the sequence like I expected them to. Oh, so there's Rev 3. This is a fully functional Apple IIe computer based on Omega 2 with additional capabilities. However, I wasn't done yet. Yeah, I forgot I had that, so I'm going to just take that off. And trust me, it totally works. So I based it off of the 2E design, obviously. I wanted to make the keyboard functional, but I gave up that a long time ago. My size goal was I had wanted to make it fit on top of the floppy drive, but because of the ports on the back, it just naturally had to be this wide. I know this, also I had a custom keyboard made that includes macro keys for things like print and the reboot, also control delete works, stuff like that. Now I realize this is kind of fast, but I'm gonna show just a brief clip of like 8 or 9 programs running to prove that it actually does run Apple II software. I probably have to do it over here now. Okay. There we go. So like that's VisiCalc, Merlin 8, Apple II desktop, number munchers, of course, Prince of Persia, and then the Mega 2. Apologize. I know it's annoying when people walk back and forth across the stage, and I try to limit it, but okay. I'll just give up. Actually, this might work. Actually, I want to go out order. So one thing I wanted to mention real quick is I said I built this, and I probably said I a bunch of times in this. I did live stream the majority of this project over like a period of almost 2 years. So there's a lot of people who helped in various ways. Some people just, they provided some code. Some people provided hardware. A lot of the people on this list just gave me encouragement when I was not in my best of moods. And so, by the way, if your name is on here, please come see me tonight. And then, God, really, why does that work? But so I have a couple of takeaways. Number one, when I first started doing, the Mega 2 is a fully functional computer. I know how to use PowerPoint, I promise. I thought this project was impossible when I first started it. I just want to remind you that if you have a project you want to do that you think is impossible, with the right amount of time, education, and help, it is possible. And I very much learned the value of asking people for help. In addition to the people on that screen, there were tons of people in the Apple II community that provided tons of guidance. It was always interesting because they'd ask me, well, what are you working on? And it's like I try to explain it, and they're like, okay. And then just a couple other things. I do run a GitHub repo that's called BitPreserve. It has vintage computer schematics redrawn in KiCad. If you need a vintage computer schematic, good place to go check. If you want a reason to use KiCad and get better at it, a great way to learn how to make schematics. And then on Thursdays at 6 p.m. on YouTube, I do stream when I work on this project. So I try very hard to give very good advice during that stream and not at all make mistakes. Later this month, there will be an Element 14 Presents video of this project. I go into much deeper detail of the challenges of Rev 2 and 3. So I just briefly skimmed over them in this. And with that, thank you. I really appreciate being able to talk about this one.